And then I'd like to invite our next speaker to the floor, Dr. Mario Villalon from Eurogroup Laminations. And so, of course, normally we thank the speaker after the presentation, but here we already can thank the speaker before, because for your hosting of the wonderful party last night, which was very impressive, and all of us have very much enjoyed. So we thank you and your company for hosting us.
Thank you, Leo. Hi, everybody. I will be presenting a new perspective, experimental approach on glue bonding. I have to spend 1 minute on every slide, so I'm going to jump in right away. So basically, Eurogroup is an early player in the glue bonding of electrical steel. We're doing this since 2015, and the approach we have followed is to test and try to validate products in terms of their magnetic efficiency. This is a cartoon we did to show how one of our technology works. During the conference, I will thank our excellent team that we have in the audience that have been filing for great patents that we have in our company, and I will tell you when this is one of the technologies that we have in our group. The argument that we carry to our customer, it is that it is beneficial to change from welding that you see in this slide in red, performance to glue bonding that you see in the middle in green. It is exactly the same material, but because you avoid damaging with welding and interlocks, now you get all the benefit out of the material. These are experimental results, BH curve, polarization on the top, and core loss at the bottom. I will say a little bit more later about these core loss maps, but they were made with one of our test bench that was also patented by EGLA. On the right side, you see the full argument. So because now you have such an improvement in efficiency, the customer can make decisions into where he can find reductions in costs. So maybe he wants to keep these great core loss reductions, and that is fine. They will keep that same electrical steel they started with and keep the improvement. But maybe they don't need that such a great improvement, and then they can just change the thickness and opt for a cheaper material. In the example I'm giving in the box on the right side, we're changing a 0.20 millimeter thickness for a 0.30 millimeter thickness that is core loss equivalent, but even there the BH curve is better with the glue bonded option. And you can change a 0.25 for a 0.35, you will still have a better polarization because you're not damaging with the welding your material. So this is the argument that I wanted to give as an introduction. And this is the real content that I want to bring today. A little bit what you're going to find in the book that Rina is printing so generously for us. I did add some information for my friend for Stefan Helfert. I don't know if he came today, but let's see if he comes. So the idea is to test mechanical performance of glue bonding products, glue bonded products. Why? Because today we're not speaking about welding anymore. Today, everybody wants to glue bond. And the argument that the study is offering is that it's not just glue bonding. We want to know how to glue bond and what material should we use if there is a difference. How do we adjust? And this is the equation we would like to use. We want to speak about stiffness. We want to speak about damping. That comes into the equation of motion that uses the external force from the magnetic, induction that we produce in the electrical machine. We used an open source design that you know very well from a California company, which I cannot state the name by contract, but is one of our oldest customer. And we took their, let's say, samples and built full stack size glue dot bonding, and then modified them with a sealing technique that was brought in from the composite material realm. It is called vacuum infusion, and I have to thank Enrique Martinez for his great contribution to the company. He patented this process. And we also used another process that is called print core pack to make the full surface. So we can use this with any kind of adhesive system. So it is, you have to imagine that you're printing like in the newspaper industry. This is one other technology that I have to thank Massimiliano and Davide Verri, who are here with us, who have patented also this technology for EGLA. The kind of tests that we do are, so maybe the sound is not there, but this is a free state vibration test where you want to hear, the resonance and the modes of vibration on the free state. And then we're going also to measure the vibration on the magnetic test bench, which I'm going to talk about a little bit later. We want also to compare the strength of these adhesive systems. So how strong are they? That is an important question, because customers, they were accustomed to use welding, which is very strong. And so in their assembly line, they're just throwing the stacks everywhere. But now we're presenting a fragile product. And that has to be said, because magnetically speaking, it is beneficial. And you will understand why a little bit later. Now, in terms of magnetics, the test benches that we are using are obviously the famous and very good Brockhaus. Where is Siebert? I have to thank you, Siebert. Maybe the party was too heavy yesterday. So yes, we do have all the Brockhaus equipment, both in our plants in Mexico, in Italy, everywhere. And we do use it because it is fast track, easy to use, very kind. But in EGLA, we have developed a particular test bench, the one you see there, based on an electromagnet inside of the internal diameter that allows to go through the teeth, which is the bottleneck in terms of magnetic flux. And then I have to thank Dr. Roberto Salas, our mathematician, who modeled and designed this patent and filed it with Enrique Martinez for EGLA Group. Thank you, guys. And so let's look at the results. This is a acoustic measurement made on the free state, full stack size, bonded with those different approaches. So the first one is the glue dot, then the glue sealing, full surface with one adhesive system, and then with another. So the first one is an acrylate-based system, applied full surface, and the other one is the epoxy, that you had the chance to see yesterday. I don't know if Stefano arrived finally. Maybe not. The party was really hard yesterday on us. So the thing is that I just wanted to tell you this. And stiffness will play on the frequency. So here I will ask you to stretch a little bit your memory and remember these old clocks on the churches. When you hit on them, they will ring for a long time because they are dissipating energy for a long time. But if you imagine that the sound is stopped, that is what we would like to see. Or maybe the frequency is changed because the shape of the bell is different, and this is what we're looking at in this slide, because it is exactly the same product. The frequency has been changed only because you're changing the adhesive system. And now the glue sealing, as you can see, is reducing the frequency, and that is very interesting because it reduces the stiffness. We will see later what does that mean on the electromagnetic efficiency. In terms of damping, you can measure damping on these graph in the free state again, and measure how fast does the negative exponential goes. So we take the natural logarithm and take the damping factor. And you will see here that the best damping is again the glue dot with the sealing around it. And that has to do with the natural modes of vibration, because we sealed it and we stopped one of those modes of vibration. It's like when you play music and you decided which note you want to play. So the others are more or less the same, except for the full surface number 2, which is the epoxy, which is very strong, cured in an oven, and then maybe it is too stiff, maybe it does not have the expected damping effect we might want to have. Now we put the stack on the test bench. As you see in the image, you have the electromagnet in the middle, and it is like inside of the machine, and you have the typical sound of that you hear in an EV machine. And that is what we're measuring, and we're focused on the first mode of vibration, and you can see there that the intensity tells us something about both things. The frequency will tell us something about the stiffness, and the height, or also the width or bandwidth we call it, will tell us something about the damping. Again, if I look at glue dot sealing, the damping appears to be very interesting for us. The argument we're making here, it is that we can print with our newspaper kind of patent your name on the surface of the e-steel, and that's the approach I would like to get to. Now, in terms of pull-off test, which is the strongest, now we're speaking about the fragility of the product. You see that the full surface, they went so strong that now you're breaking the adhesive tape. The part is not breaking. It is the adhesive tape that is detaching, and I cannot say more than that, so I'm at the maximum value. I don't want to be there. I want to be below, like the two first parts. I prefer to have a little bit more fragile product. Why? Because of these kind of results. The first one is the BH curve that we produce with the Brockhaus. We like to produce this result with the Brockhaus. It gives the polarization, and you can see from the slope a very big difference in permeability. Again, it is exactly the same lamination with exactly the same thickness. The only difference is the approach, the design of the glue, and for the two full surface, you have one that is an acrylate, the other one is an epoxy that was left to cure in an oven for 1 hour. So it became very stiff, very strong, the kind of product we're asked to. And in red, you see the old welding conventional technique that we used to use, and then you see how suddenly, if you start putting it too strong a glue, then again, you're going back to welding, so maybe the argument does not stand anymore, and just go back to welding, guys. You know what I mean? So that's one point. With the Brockhaus, you can also measure core losses, and obviously these core losses do not match exactly what you're used to see in the Epstein test, because this is a big full stack, full size stack. So the numbers are different, but you can use it to compare one with the other. And again, it is the same tendency that you see. The glue dot that we use in mass scale production has a very interesting core loss. Then if you seal it for some harmonic reason, it improves. But then if you put too much glue, it goes worse. And if you cure that glue and make it stronger, it still goes worse. But in core loss, you do not go that far as going back to welding. In red, you see the big core loss for welding. Now, you see in the image on the left side that the flux with the Brockhaus equipment do not go through the teeth. And that is why we prefer to use Dr. Enrique and Dr. Roberto invention. That is another test bench where we go through the bottleneck with the flux. And you see that now the sensitivity is different. Okay, so these are the kind of core losses that we like to measure. It produces a map, goes up to whatever frequency you want to go. With these very big stacks, you cannot go to 1,000, 2,000 hertz. It takes lots of energy, and it doesn't make sense. 800 hertz is already very high, so you have there the comparison. We would like to use 400 hertz, which should correspond to l'autostrade, how do you say, the highway driving cycle. Okay, 400 hertz. And then you have basically the behavior we expected to see. And finally, just to go a little bit beyond, you must know these guys. So we have here Steinmetz. 100 years ago, he was working for General Electric, and he sat with Henry Ford. Henry Ford had problems with his generator, and called Steinmetz from General Electric, and Steinmetz sat there with him, and Henry told him, what do you need to work? And he said, well, a table, a pen, and some paper. And the only thing this guy did was to listen. He sat there and listened to the big generator that he had in front of him. It was to produce energy in Henry Ford Company. And he was listening, and after 1 week, he said, okay, guys, behind that panel, you will remove 6 turns of copper, close it back, and you will have no more vibration. So that is something inspired that I like to tell. 100 later, we went to Torino with Leonardo, who I would like to also thank because he is our top sponsor. He is our automotive CEO and vice president at EGLA. So I'm not the one, Leo, who should, this Leo, not the other one, who you should thank. It is Leonardo Franchini, who you should thank for yesterday's big party. We sat with Bertotti, and let me tell you, just between us, he was crying a little bit of emotion when we told him that we were using his equations, his coefficient, to go a little bit deeper in what we are doing. So what we do is to take the maps produced with our test bench that are a little bit more accurate because they go through the teeth, isn't it? And then we just fit them, 3D fitting, and that produces these coefficients that we like to study. And we are interested in looking at the change because we're comparing one thing with another. And as a conclusion, Leo, because it looks like I'm done in 2 minutes. As a conclusion, what came out from that study, it is this big table. So you have the stiffness for those 4 cases that we stated at the beginning, glue dot sealing, full surface with an acrylate glue system, which we have developed with different suppliers, and full surface with an epoxy that can be cured longer or less time. We have to adjust. I'm not saying not to use it. I say we have to be wise when we use it. And then you have the stiffness, you have the damping, vibration intensity. You will see that the glue dot sealing is the most interesting there. And then you want to compare that with the magnetic efficiency result on the right side of the table and going back to the equation. Now, what we're doing on the lower part is to take an analytical equation and compare it with a parametric equation. That is not fair, isn't it? But it is useful. So what do we see? It is that damping, the little c in the equation of motion, could relate very well to the first term in the Bertotti equation that relates to hysteresis and to excess loss, which we believe, at least that is what we heard in Milan 2 years ago, that excess loss today we believe has to do with surface effects. So for me that makes lots of sense. Okay, damping would play a little bit with surface tension, and then we could ask, would that be magnetostriction? Okay, and then the stiffness, that is the last term in the equation of motion, plays with the hysteresis, but also with eddy current for a given reason, and we have to ask why. We have to study a little bit more that matter. So, in conclusion, glue bonding can modulate the mechanical behavior through stiffness and damping. Vibro-acoustic and noise measurement allows measuring accurately glue bonding effects on stator core stacks. Magnetic performance correlates with the vibro-acoustic mechanical performance, and Steinman's Bertotti coefficients allowed showing decoupling effects, decoupling the effects from high stiffness bonding. I think I maybe did a mistake there. So guys, thank you very much, and you're welcome.
Thanks a lot, Mario, for a very insightful presentation, which is now open for questions. Pablo.
Thank you, Mario. Very nice presentation. I don't know if it's a question or if it's a comment, but okay, I would like to share with you. The term of the stiffness, is it related to the Young modulus of the system?
Is that the question?
That's just to introduce. So that stiffness that you are commenting is related to the mechanical Young modulus of
yes, it is the Hooke constant in the equation of movement.
So what it would be the contribution of that stiffness and the Young modulus on the fatigue of the system? Let's say, I suppose that you are measuring, let's say, fresh, ready-made. What is going to be the evolution with the time, with the glue, and the metal part, you know, on this noise, vibration, the degradation with the...
That is a very interesting question. We have maybe on the streets more than 10 million motors today with this technology. And yes, we have performed aging tests every time we launch a new program, but you know that that does not tell really what happens. And what we do know, it is that the motors are just fine today. So it is aging very well. But the question you're making, and because I know you, is very difficult to answer. So maybe I will keep it in my notebook for a while, if you allow me to. Yeah.
Thank you. So we'll be interested to see your notebook 10 years from now. So other questions? If not, then I'd like to thank the speaker again. So. And it is my pleasure to call the next speaker to the floor, Erik Thijssen from MedClass, who will give a presentation with the title Manufacturing Methods for Utilizing Amorphous Electrical Steel in Transformers.